Welcome to this explainer. Okay, today we are going to take some massively intimidating industrial engineering concepts and, well, we're translating them into the hidden story behind the very clothes and fabrics you interact with every single day. You know how a brand new dress shirt has that incredibly crisp feel? Or how a basic piece of cotton can somehow be made to look exactly like shimmering silk? Well, the secret is a heavy-duty industrial process called calendaring. And honestly, it's pretty mind-blowing, so let's jump right into how it actually works. So, here is our quick roadmap for today. First, we'll look at the ultimate industrial ironing, then the anatomy of the machine, followed by solving engineering challenges, controlling the elements, real-life fabric finishes, and finally, advanced roll technology.
All right, Section 1, the ultimate industrial ironing, how pressure and heat create everyday magic.
Basically, calendaring is the ultimate industrial iron. It's a mechanical finishing process where raw fabric gets compressed by passing between two or more massive rolls under incredibly controlled conditions. We're talking highly specific time, temperature, and pressure. Before a piece of cloth can become your favorite smooth bedsheet or that water-resistant jacket you love, it absolutely has to endure these immense, highly regulated forces.
So, what's the actual point of doing this? The crucial thing to understand is that this process solves the basic problem of rough, airy, unfinished material. By squishing the fabric, you give it a smooth, silky touch. You're literally compressing it, reducing the thickness, and squeezing those woven threads incredibly close together. In real-life terms, that reduced air permeability transforms a standard, breezy weave into an impenetrable windbreaker or a piece of dense sailcloth. Plus, it dramatically increases the fabric's luster, making it shine, and can even stamp permanent 3D patterns right onto the surface.
Moving on to Section 2, Anatomy of the Machine. The bowls that make the magic happen.
Now this is where it gets really interesting. You absolutely need a contrast here, specifically between metal bowls and resilient bowls. The metal bowls, which are usually polished steel or cast iron, bring the heat and that brutal, hard surface needed for a high shine or a 3D effect. But think about it. If you just smashed delicate fabric between two heavy steel rollers, you'd completely crush and destroy the fibers, right? That's exactly why the opposing bowl, the resilient one, is made of tightly packed cotton, paper, or synthetic rubber. It gives the fabric just enough of a cushion to press into without getting ruined.
And this beautifully highlights what we call the knit point. That's the exact line of contact where the fabric squeezes right between these contrasting rolls. You can see the raw fabric going in, getting pinched tightly between that hot steel roll on top and the softer, resilient roll beneath it, and then coming out permanently flattened. It is literally being ironed flawlessly in just a fraction of a second.
Which brings us to Section 3, Solving Engineering Challenges. Physics under pressure.
I want you to just imagine applying 50 to 100 tons of pressure straight down onto a single machine roller. To put that into perspective, that is the equivalent weight of dozens of average-sized cars resting entirely on one metal cylinder, which is pressing down on a delicate piece of cloth.
So under that kind of extreme load, you run into a massive engineering problem. The middle of the roll actually bends and deflects slightly away from the pressure. If you look at diagram B, you'll see how this deflection causes uneven pressure. It gets tight on the edges, but loose in the middle. Obviously, that would totally ruin the fabric. But engineers are clever. They solved this with a technique called cambering, which you can see in diagram C. They literally machine the resting roll so it's slightly thicker, sort of bulging right in the center. That way, when those 100 tons push down, the roll bends exactly into a perfectly straight, flat line.
Another absolute genius solution for this exact same problem is roll skewing. Instead of changing the physical shape of the bowl, they position the massive cylinders slightly crossways, or skewed, against each other. This little geometry trick ensures the pressure line remains perfectly even across the entire width of the machine. Without this invisible high-level math, those wide, perfectly smooth bed sheets you sleep on, they simply wouldn't exist.
Let's look at Section 4, Controlling the Elements. Speed, heat, and precision.
Depending on what the fabric is made of, operators use gas, electricity, or steam to heat these metal bowls up to a scorching 300 degrees Celsius. And that extreme heat is absolutely vital for processing synthetic materials. It melts them just enough to bond the fibers together, which is exactly how we get that incredibly durable, windproof outdoor gear and tough sailcloths.
Now, while the older machines used basic screw systems to apply pressure, modern calendars use highly sophisticated pneumatic and hydraulic systems to adjust the weight dynamically. They also use these super accurate thyristor motor controls to manage the speed. We're talking anywhere from a crawling 5 meters per minute up to a blazing 75 meters per minute. The basic rule of thumb here, slower speeds equal a longer time trapped inside that high-pressure nip, which gives you a much more dramatic flattening effect on the final fabric.
All right, Section 5, Real-Life Fabric Finishes. From the machine directly to your wardrobe.
Let's say you want a highly polished, glossy fabric, what's known as a chintz or glazing finish. To get that, you use a technique called friction calendaring. This is where you intentionally run the heated metal bowl up to 300% faster than the actual fabric passing beneath it. It's kind of like polishing a pair of leather shoes with a fast-moving cloth. The machine is literally buffing and polishing the fabric's surface to a high-gloss shine. The really cool part is that just by swapping out a roller, you can completely change the fabric's identity. Take Schreiner finishing, for example. This technique uses a bowl engraved with microscopic, fine lines tilted at exactly a 30-degree angle. When that gets pressed into plain old cotton, it catches the light perfectly, giving it this beautiful, permanent, silk-like appearance. So, if you've ever seen those luxurious, silky-looking drapes, curtains, or local camise shalwar suits that are actually 100% cotton, you are experiencing the magic of a Schreiner finish firsthand.
Then there's the embossing finish. Here, the heated top metal bowl is deeply engraved with a pattern, like that beautiful floral design you see right there. As the fabric passes through, the intense heat and pressure physically stamp that 3D pattern right into the material. You see this all the time in home textiles, fancy linens, and specialized upholstery.
Finally, Section 6, Advanced Roll Technology, the future of textile engineering.
So remember that 100-ton bending roll problem we talked about earlier? Well, modern engineering solved it dynamically with something called the S-roll. It basically acts like a swimming roll. Instead of being solid metal, the steel tube actually rotates around a fixed inner axle, and the space between them is filled with pressurized hydraulic oil. By tweaking that oil pressure on the fly, the machine actively pushes back against the bending forces in real time, guaranteeing perfectly even force. This level of absolute perfection is absolutely critical when you're manufacturing life-saving, low-permeability technical fabrics. Because let's face it, when you're making parachute silk, you really cannot afford an uneven weave.
And it gets even more advanced with the Hycon system. Looking at these cross-section diagrams, you can see it actually replaces that internal pool of pressurized oil with a row of individual hydrostatic pistons mounted straight onto the axle. This lets operators adjust the pressing force locally, literally zone by zone across the entire width of the machine with insane computer-guided precision.
The ultimate party trick of this Hycon roll is all about those precise pressure zones. Because of how it's designed, the fabric can pass through the machine and get two totally different effects in one single continuous step. It can hit one pressure zone for a high, glossy glaze, and then loop right back through a softer zone to get a beautifully soft handle. It literally cuts production time in half while creating an incredibly luxurious feel for things like high-end shirts and linens.
It really makes you wonder about the massive, invisible world hidden inside our everyday routines, doesn't it? Next time you slide into a set of perfectly smooth hotel bed sheets or zip up your favorite windbreaker, I really hope you'll take a second to appreciate the 100 tons of crushing weight, the 300-degree scorching heat, and the brilliant mechanical engineering that brought that simple comfort to life. Thank you so much for joining me on this explainer, and definitely keep your curiosity alive.